Yeah, okay. Good. Yeah, thank you very much. I'm head of the human-machine interaction group here at Aalborg University and also director of the HRI lab at the tech faculty. And what I will talk about today is mainly about this HRI work. And I feel a little bit like the odd one out because I will not talk so much about natural language processing, but more about human-robot trust. But in the end, we will see that NLP might play a role in that. So why are we interested in that topic? Well, the thing is that in the different application areas and projects we work on, we always come to the point where we have to look at why are people not using the system as they are supposed to do, or why are they trusting it too much and expect too much from the system. And we saw that we can that trust is a good way of describing these problems. And I just brought some examples here. So if you look, for instance, on the top left side, we have collaboration in production environments. So it's a project we're currently starting up. It's called DrapeBot, and it's about collaborative draping of carbon fibers. And there we have the issue that the worker will be collaborating with the rather large industry robot, so not a collaborative robot, but we still have to be close to the robot and do the draping together with the robot. So there is an issue of safety, of course, but there's also the issue from the worker of trusting the system that it actually does what it should, and how can we make sure about that. We have other areas, for instance, health. We see the exoskeleton down there, or on the right bottom, there's a system that we tried in the neurocenter here in the region, where it's a kind of educational game where adolescents with cerebral palsy try to control these robot cars and drive to certain goals. And because of their condition, they have sometimes problems in really controlling these cars. So the idea is that the cars adapt to their abilities and take over some of the navigation tasks to level the playing field between different players. And again, there we have kind of collaboration, or in this case, maybe shared control, shared decision making. And again, it's about trust. So if the robot car suddenly does something unexpected, although you seemingly seem to control it, that creates quite a tension in this interaction. So different areas where we stumble upon this problem. And then we looked at, obviously, what has been done there. And we see that trust in automation is, of course, a topic since a very long time, 20, 30 years. A lot of research has been done. But if we look at that, we see what also Chen told us about the robotic part there. We are focused on the task completion, on the task success, and not taking so much into account what happens on the side of the user, the human operator. So it focuses on the task, and the trust measures that we find in the literature are actually used as a kind of static evaluation criteria for the system. So we have the system. We measure the trust level of the user to the system. If that doesn't match, then we do a little redesign of the system to get this in line. But that's not really what happens when we interact with robots, right? Because they do not just do, at least we're moving there, they do not just do one task and that's it. So they are flexible, it's dynamic. We have just seen examples where we don't really know what the task will be, and this is somehow negotiated in the interaction between the operator and the robot. So we cannot really go with this very static way of looking at trust. And if we look at trust from a human factors perspective, then we see it's a kind of multidimensional psychological attitude. There are beliefs and expectations involved, uncertainty, risk, obviously a big part. And of course, it involves different types of processes because it develops over time. And that's also something that's interesting if we look at interactive systems like these robots. So what we want to do, or what's our goal, is to somehow calibrate the trust, like we can see it here, right? So we assume that we have an actual trustworthiness of the system, so we know to which extent we can trust the system to do what it should do. But on the other hand, we have the user or operator that perceives the subjective trust towards the system. And we want to hit this sweet spot in the middle, this corridor of calibrated trust, where this matches, right? But for that problem, or for that to work, we sometimes have to dampen the trust level of the user if they are over positive about the system, or we have to repair trust if they do not trust the system enough. And that's quite interesting because actually we don't really know what the parameters are that determine the robot's trustworthiness, right? So we have some ideas, of course. We can find some parameters in the literature for automation, but if we look at interactive robots, collaborative robots, we're not quite clear what the parameters are that we look at there. We don't really know how we measure this perceived trustworthiness. And again, we have measurements from trust in automation, but they are usually post-hoc subjective questionnaires. And that doesn't help us if we are in the interaction with the robot. So we need some kind of dynamic real-time measures for it. And then, of course, how do we do that, right? So how do we actually damp the trust, or how do we repair the trust? If we find that there is a problem. So this is the space in which we are working with this topic of trust repair, and I will just quickly present two studies that we've run where we looked at different factors that look at this. So if we look at the trust assessment, then I just said we need some kind of trust assessment that is based on the interaction and based on the observations, the sensor data that we can get in, and that we can then relate to an interpretation of the trust level of the user. And there are a lot of interesting parameters that we could look at. And speech is one, especially if we look at paralinguistic features, maybe at the semantics, that could be interesting. But there are a lot of other elements, and we usually look at multimodal signals. So we would like to combine different signals, like the body movements, the facial expressions. We could look at physiological signals, like we just see here in the picture, where we go for GSR, skin conductivity, as one of the features. But to develop a trust assessment tool, we need to somehow relate these measurements to the trust levels of the user. And to do that in a principled way, we need to be able to manipulate the trust level of the user in the experiment so that we can make this connection and that we know which trust level the user will be in. So there are a lot of different parameters that we have to look at there. For instance, the risk factor in the experiments, the robot behavior, the communication, and so on. So, and one thing we looked at so far is the risk factors, where we ran an experiment that investigates 3 different risk factors. And the first one was, we call it task specific. So there are tasks that have more risk in them than others. And here we set up a task where the robot gives a cup of water to the participant or some Lego blocks. And obviously the water task is more risky because you can actually get wet. And then we have behavior risk. So that has to do with how the robot behaves. And there we just looked at one parameter, and it was the speed. So how does the trust perception change when the robot is going at a low versus a high speed? And of course, there are interactions between the task risk and the speed, right? And then we looked at contextual risk, which has to do with the environment in which the robot is situated. And we looked at beside versus behind the operator. And we see some nice screenshots, what happens when the robot sits behind you and comes from behind and takes something from the table. So people get a little bit frightened. Interestingly enough, that doesn't show in their subjective impression of the trust towards the robot. So what we see is we have a significant effect in relation to the to the inherent and behavior risks, but it's unconclusive in terms of the contextual risk. Although if we look at the people when they do it, we see that there are quite strong differences if you look, for instance, their facial expressions or their movements when the robot is operating. So that also shows us these questionnaires are not everything that's not the standard that we are looking for. So we need to also look at these other factors here. But based on that, we just picked the behavior risk factor and set up an experiment because we wanted to know more precisely how we could manipulate the trust level using this feature. And we set up an experiment where the user supports the robot in drawing something. So we have a very close proximity interaction here. And then we tested different speed conditions. And in the first one, we start with a slow speed. And then at one point in the interaction, we increase the speed. So we disrupt this experience that we have. And you can see that in the upper part of the diagram. And then in the other condition, we start fast. And then we go slower in the middle of the experience. And what we can see is that in both cases, when this disruption happens, we actually have an effect in the trust measurements, which is much stronger when the robot suddenly moves faster, but it's still significant when we look at the case where the robot moves slower. What we also see with this is that trust is gradually developing, right? So that's on the left side of the disruption. So the trust levels get higher and higher in general. Right? And then after the disruption, we have a drop, but then we also have kind of repair, right? So we go up again. So we get some information about the dynamics of this trust development. So this tells us we can actually use these behavioral parameters to manipulate the trust level of the user, and having this information, we now can actually look at relating features that we can observe, and we started with gesture and movement features as trust assessment tools. So what about natural language processing? So this is all very well, right? But we haven't talked about language yet. And actually, we haven't looked at that yet. But what we can see is, so we looked at nonverbal indicators of trust. That was body movement, postures, gestures, facial expressions, and so on. But what we see from the experiments that we have run so far, and I just showed 2 of them, right? So we see that language seems to be a very good indicator actually for trust. Because in the trust assessment studies that we've run, we see these emotional reactions when trust is disrupted. And that can both go in a negative way, that we see apprehension or stress, or that can be in a let's say positive way, that people are amused when something goes wrong, depending on the task they are doing. And this also shows what they say and how they communicate. So that would be an interesting aspect to go for. And we've earlier shown, so I brought a very old paper from 2015 where we looked actually at emotion recognition from paralinguistic features in speech. Where we could show that we can actually recognize the emotional state of the user from the speech signal, and in that case we also combine it with some physiological measurements, so we get an actually better interpretation of that. But it's possible, and it might be a good way to go and to correlate with the trust assessment. And then trust calibration is the other part, right? And there Casper has just run an experiment where we looked at the explanation depth in what the robot tells the operator, why something didn't went as it was expected to go, and looks at how can we manipulate what the robot is communicating in order to calibrate the trust level of the user. that was my 10 minutes. So thank you very much. Here are the people that actually do the work while I present, and you can have a look at our websites if you're interested. Or we also have a LinkedIn channel now where we post news if that is interesting for you. Thank you very much.